Remember that for any limit, we're just being asked what y value is being approached from the left and the right as we are getting closer and closer to an x value. So for this first example, the limit as x approaches 3, we're trying to see what y value are we approaching from the left and the right as we get closer and closer to 3. So if we're trying to figure this out algebraically, it does help to think about what it looks like graphically. So for something like this, it's just a parabola. So it makes sense that at 3, it should be approaching the same thing from the left and the right. There aren't any holes or asymptotes, things like that, no jumps. So if I'm wanting to know what value is being approached when x is 3, I can simply plug in 3 into that expression and see that since f of 3 is 10, then our limit as x approaches 3 has to be 10 as well. But if we're dealing with a function that is not continuous, maybe it has a hole, a jump, an asymptote, something like that, when I plug in 3 into this next equation, notice that I would get 0 on the top and 0 on the bottom. So I'd end up with 0 over 0, which we call an indeterminate form. And basically an indeterminate form says that there is something that I can do with my equation here where I simplify it and I'm able to plug in the 3. So that 0 over 0 actually tells me I can simplify it. There's some way that I could approach this. So for this one, maybe you've already noticed that we can factor the numerator. And once we've factored it, we can cancel the x minus 3's, and now, just like the one at the top, I can plug in 3 into my equation and find that the limit as x approaches 3 of my function is actually 6. So if we remember back to rationals, because this x minus 3 canceled, that's what tells us that there was a hole at x equals 3, which makes sense. We couldn't plug in the 3 at the beginning because there was a hole there. But once we eliminate it, we can see that's actually where that value is. So we're looking at a situation where at x equals 3, we're approaching a value of 6 from the left and from the right, but there is actually a hole at 3, which means the function may not exist, but the limit does. So we have a lot of different types of limits, but in general, we want to start by plugging in the value for the limit. So for both of these, we began by plugging in that 3. And then from there, if we get a value, we get a value. But if we get 0 over 0, then we can simplify by eliminating whatever that issue is. We're going to go over different ways to simplify. Once you have it simplified, you're going to plug in the value again, like we did on that second example. So all of our examples today are coming from the even numbers in your textbook, so you can refer back to the page number that the assignment is on, page 870. This is number 8. We're looking at the limit as x approaches -2. So remember, our first step always is plugging in that -2 into numerator, denominator, and we are going to end up with a 0 over 0. So that's what tells me I should be able to simplify, and this is similar to that last problem where I can factor the numerator and I should be able to cancel an x plus 2. So this is a different type of factoring, so I might go off to the side and look at my factoring where I'm multiplying my first and my last number to get that -4, trying to split up that middle term by looking for numbers that multiply to be -4 but add to be a +3. So it looks like a +4 and the -1 will do the trick. So splitting up that 3x into a 4x and a -x, and then factoring by grouping, so taking out a 2x in the first part, and then a -1 out of the second two terms. Remember that that repeated part is one of the factors, and then what we factored out makes up the second factor. Okay, so now that we have factored the numerator, we can return back to the limit, and we're looking at x plus 2, 2x minus 1, or x plus 2 in the denominator, canceling both of those. And now I can actually evaluate the limit by plugging in -2, and I get something that is not an indeterminate form. So my limit ends up being -5. For number 16, again, when I go to find that limit at 0, I will end up with the square root of 4 is 2 minus 2, so 0 over 0. So this tells me I can simplify it, but this is not something that is easy to factor. So I have a different strategy here where if I'm trying to get rid of an issue with radicals, we've done this in the past with simplifying, where I want to multiply by the conjugate, which is just this whole expression, but changing that sign in the middle to be plus instead of minus. We do have to multiply the top and the bottom by the conjugate because we can't change the value of this. We want to multiply it by 1, and that's what we're doing here. So we've now got the limit as x approaches 0. This seems kind of gross, but it actually works out really nicely because when I multiply radical x plus 4 and radical x plus 4, I just get x plus 4 because it's kind of like x plus 4 squared, square rooted. And then because these are a difference of squares, I will end up with the middle terms going away. So I've got a 2 radical x plus 4, a -2 radical x plus 4, so those cancel. And then my last would be this -2 times 2, so it would be a -4. In the denominator, I don't want to actually multiply, I just want to kind of mock multiply, where I've got x times this x plus 4 plus 2, because what's going to happen, and you might already see what's happening here, my 4 minus 4 is going to cancel, and then I'm left with only an x in the numerator, where I can cancel it with the x in the denominator. So now I'm looking at the limit as x approaches 0 of 1 over. So I didn't want to multiply it all out because then I would just need to factor out the x in order to cancel. But now I can go ahead and plug in my 0. I'll have this 1 over, this radical 4 is just 2 plus 2. So I've got 1/4. For number 22, again, when I plug in 0 at the beginning, my 1/4 minus 1/4 is 0 over 0, so I can simplify it in some way, but it's not that factoring type and it doesn't have a radical in it. So something that I can do is go ahead and get a common denominator in the numerator and go ahead and subtract these two fractions and see what happens. So when I get a common denominator, this is going to be lacking that 4 minus x. So 4 minus x over 4 minus x. This side is going to be lacking a 4 in the denominator, so 4 times 4. So that means I'll have a 4 on this side and then minus 4 plus x with a denominator of 4 minus x. And then still x in the mega fractions denominator. Okay, so some things that we might notice here, we still have that situation where the 4's are going to subtract, kind of like in that last one, where we're left with just an x in the numerator. And then we want to go ahead and take this x that's in the very bottom and flip it to multiply. So since it's an x over 1, I can flip it and multiply to where I have a 1 over x. Once I cancel the x's, now I can plug in 0. So in the numerator, I'll just have 1. Once I plug in 0, I'm left with a 4 times 4. So I'll have 1/16. For number 26, we have trig in our limits, which, don't panic, a lot of times with trig functions, if you just plug in the value, you actually will end up with the limit. It'll be something continuous. That is actually not the case with this one. When we plug in pi over 2 into both, we are going to get 0 over 0. So in order to use like an identity, something like that, I need this to, one of them, to have a squared in it. So this is going to be kind of like the radical problem where I'm wanting to multiply by the conjugate of the top. So a 1 plus sine x. That way it can look something like one of our Pythagorean identities. So I'll have a 1 minus sine squared x in the numerator. Remember, because one's plus and one's minus, I'll have that minus sign and the plus sign in the middle here that cancel. And then in the denominator, just like I did with the radical, I'm going to mock multiply, where I'm not really multiplying everything out, just putting them next to each other. So now I can use the fact that 1 minus sine squared, think back to our Pythagorean identities, is equal to cosine squared. It's like we subtracted the sine squared from the other side. And then we are able to cancel one of those cosines. So we've got a cosine in the top, and then a 1 plus sign in the bottom. And usually once you've canceled something, you are good to go. So at this point, I'm going to go ahead and plug in my pi over 2. Cosine of pi over 2 is 0. And then it really doesn't matter here as long as it's a value, but sine of pi over 2 is 1, so my denominator is 2, which makes our limit 0.